Yes. The first
I
one.
need to share my I
Mm-hmm.
need to share my screen.
Yeah.
So I mean, you have to give me permission for that.
Okay. Okay. Can you let me know if you can right now?
Sure. I think yeah. I think I can.
Okay.
Okay. So last time we derived a Schwarzschild metric around a spherically symmetric solution of Einstein's field equations. In this lecture, we're gonna do a number of things. One of the things that we're gonna do is to investigate how particles move in the Schwarzschild geometry, right? So if we want to investigate that how particles move in Schwarzschild geometry, we have to solve the geodesic equation. So So what is geodesic equation? In the last lecture, I wrote two different forms of geodesic equation. One of the forms involved Christoffel symbols, which is like this. But there's another form that people write. The other form is like this. And I did write this form in the last lecture as well. So this is like that, right? So we're going to use this form of the geodesic. There is one index which is free, which is alpha, right? So let's put alpha equal to 0, which means that you are talking about the time component now. So the geodesic equation becomes something like this. And you see that here you will have a time derivative of the metric. But we do know that for Schwarzschild geometry, the time derivative of any metric component is 0. So it means that this side will be 0 because, uh, or as this is 0. Let me just put it separately. Okay. So this is the first geodesic equation that we get for the Schwarzschild solution. Now, if I remind you what the Schwarzschild solution is, it's something like this. And if you remember, I used this notation last time, and I explained that this is called a solid angle squared. Sorry, this is equal to this thing plus this thing, right? So I'm going to use this again and again whenever I don't care about the angular coordinates. Okay, there is one additional piece of notation that I want to introduce. So I told you that this radius, uh, r equal to 2gm, is called the Schwarzschild radius. And we have a different notation for it, which it is referred to as rs, right? So it means that this time component for the Schwarzschild metric can be written as this. So time component. So now let's use this time component, which is given here in this geodesic equation. And let's see what happens. So it becomes 1 d over d tau minus 1 minus rs over r times dt over d tau equal to 0. But you can multiply on both sides with the minus 1 and you get this thing, right? So now if the thing is, if this particular thing has a 0 derivative with respect to the proper time, it means that it's constant, right? So it means that 1 minus rs over r times dt over d tau is a constant, and let's call that constant E, right? Now, what is this E? This E is sometimes called a relativistic energy. per unit mass. I mean, the interpretation is not that important right now, but the important thing is that it's a constant, right? Now, what does this equation tell you? Well, if you remember, t is the time coordinate that you use for the Schwarzschild geometry. But is it a time? Well, we do know that if this is the Schwarzschild black hole, right, and if you go to a far, far distance, so when r equals infinity, we did see that at this particular time, the space becomes flat, and the Schwarzschild metric becomes, which is the metric for flat geometry. And you can see that now t is just coordinate that uh, you know um, any observer will measure at at very, very large distances. So t is the time that an observer at infinity records. Okay, so that's this important interpretation is important. Time for an observer. Time. It means that anything that's moving, any object that's moving in this geometry, uh, will have a proper time along its world line. So it means that if with itself, that particular observer will experience some time on that clock, and that particular time is the proper time, because proper time is the time that an observer records when there is no difference in the spatial coordinates. And we do know that for any observer, the coordinate of itself is not changing. So that's the time that a particular observer records, which is the proper time. So tau, which it is the proper time, it means the time that any arbitrary observer records. Okay, so what does this equation tell you now? So this equation tells you that uh, t and proper time, they are not the same, because if they were the same, their derivative with respect to each other would be 1. But that's not happening here. So as you can see that dt over d tau equals e over 1 minus rs over r, as you can see here. Now, the thing is that as r becomes bigger and bigger and bigger, so as r approaches infinity, capital T over T over dt over d tau equals E. Okay. But if r is less than infinity, which means that if r is, not that big, if it is small, then this particular thing becomes small, which means that this whole fraction becomes big. Now, what does that mean? It means that if r is finite, by the way, there is an argument to show that this E has to be 1 in many cases. So this E has to be 1 because as you can see that if R is infinity, then the observer at infinity is a bit like the observer at infinity. So T T and tau can be the same in some context, but it's not always 1. But that's not the point. The point is that if R is finite, then dt over d tau increases as R decreases. So as you can see that if R decreases, this denominator becomes smaller and smaller and smaller. If it becomes smaller, it means that this whole fraction becomes bigger. It means that this fraction becomes bigger, dt over d tau. What does that mean? It means that the time recorded by an observer at infinity can be much bigger than the proper time that any observer, is experiencing moving in this geometry. What does it mean? It means that if you have a clock, let me not erase it. Let me make a new diagram. So if this is the Schwarzschild black hole, and let me make some clocks here. So if there is a clock here at r equals infinity, And if there's a clock here at r equals some r, I don't know what, it means that the time that is recorded by, or the rate of time, that passes for this clock is, let's call it t, and the rate of time that passes here is tau because it's a moving clock. Now, what this equation tells you is that as r decreases, dt over d tau increases, which means that the closer you are to this black hole, the slower the time passes on a clock, that's near the black hole. So this particular equation is just telling you that gravity can affect the flow of time. And the thing is that this is not something that is just esoteric physics. This has practical consequences. For example, you know, if you look at the GPS satellites, the GPS satellites are at a distance from Earth, right? It means that, they are in a smaller gravitational field. Now, the difference is small as compared to the gravitational field that we experience on Earth, but the difference is not zero, of course. So, since they are in a smaller gravitational field, time passes at a quicker rate for the clocks on the GPS satellite as compared to, the time, the rate of time that, that is, sorry, the rate at which time passes on the surface of the Earth. Now, if we want the clocks on the Earth and the clocks on the GPS satellites to be synchronized, you have to correct for this difference, right? And that does happen. I mean, engineers have to correct for the difference of time that, the GPS satellite clocks and the clocks on Earth experience, right? So this is something that has practical consequences in, GPS navigation, for example. So this equation just tells you that gravity can affect the flow of time. Okay, before I move on, let me see if there are some questions. How do we know if the singularity we have is an actual? We will come to that. Okay, so there are many ways, but one good way could be computing the Krushman scalar. Which, yeah, I will come to these particular points. Is there any place inside or on the Schwarzschild radius with the space? We will come to those questions. But if you have any questions regarding the discussion that I'm having right now, let me know. Okay, so until now we have solved for the time component of the geodesic equation. Well, not solved, but we have discussed that. Let's talk about other components. So let's talk about the phi component. So if I remind you, the geodesic equation looks like this. If you put alpha equal to phi, you can again see that this derivative is just zero because there is no component of the metric tensor in the Schwarzschild geometry that depends on phi, right? But the left-hand side will not be zero, of course. It will be something like this. And we do know that the phi component of the Schwarzschild is just the usual r squared times sine squared theta. Now, this again means, so okay, let me write the equation first. It means that r squared sine squared phi is zero, which again means that this is the constant. And let me call this constant small l or lowercase l, right? Now, what does this equation tell you? Well, this equation is not that, complicated actually. Uh, Before I talk about this equation, let me tell you that there is the symmetry argument to show that any orbit that moves in Schwarzschild geometry should always move in a plane. It should not leave that plane. So, for example, um, if this is Schwarzschild black hole, and there is this particle that starts, with some velocity v, right? Now, now you have a vector here and you have the origin here. You can always choose a plane. Like, wait a minute. You can always choose a plane that contains this origin and that contains this velocity vector. Okay, so you can always choose a plane. Now, my claim is that this particular particle that's moving in this plane will never leave this plane. Okay, how do we say that? How do we show that? Well, the thing is that if it does leave this plane, it means that at some point it has to decide if it wants to go in this direction, which means that direction perpendicular to the plane, or It doesn't go in this direction, but it needs to have at least a component of velocity in this direction, or it needs to go in the other direction. Now, the thing is that there is no reason to choose one direction over the other. Why? Because you have spherical symmetry in the Schwarzschild, geometry. So since you have no reason to choose one direction over the other, it means that it can never have a non-zero component in the up direction or in the down direction. I mean, relative to the plane, of course, which means that it never leaves the plane that it starts from. And by the way, this is not something that's special to, general relativity. It's not something that's special to Schwarzschild geometry. It's also true in Newtonian mechanics. We do know that, if you, I don't know if you have, learned classical mechanics to that extent, but there is this topic in classical mechanics called the central force problem, which means that if you have a force that always points to a particular point, and there too, you can show that since you have spherical symmetry, because the force only depends on the radius and not on the angles, there too, you can only have orbits that move in, a plane, right? Okay. So since the motion is always happening in a plane, you can always choose coordinates. So for example, if this is the plane, you can always choose coordinates, your spherical polar coordinates like this, which means that the z direction is perpendicular to the plane in which the motion is happening. If that's the case, then this plane has a theta coordinate of pi over 2. So you can always choose coordinates such that the plane in which the motion is happening has coordinates theta equals pi over 2. And that theta never changes, right? Okay. Which means that in this equation, you can put theta equals pi over 2. So if theta equals pi over 2, that means r squared d phi over d tau equals L, right? Now, if you multiply both sides of this equation by the mass of the particle, which is m, so okay, let me do an extra step. Um, So m r squared d phi over d tau equals ml. You can see that this side just becomes the angular momentum in the, in the phi direction, which means that angular momentum about the z axis. So this becomes about z axis, all right? And you can see that this is equal to a constant, right? Which means that this L is just angular momentum per unit mass or per mass, right? So this equation, the geodesic equation in the phi component, tells you that the angular momentum in the phi direction or the angular momentum about the z-axis should be conserved. So it's nothing more than angular momentum conservation. So just remember that this L is defined like this. We will need this particular equation later. And there's another equation that we derived earlier. We will also need that equation. That equation is this. Sorry, this equation. So let me copy this equation for later use from earlier. dt over d tau equals e over 1 minus rs over r. Okay. So we have solved for, not solved, but we have discussed two different components of the geodesic equation. Okay, let me see if there are some questions. We know that from pop physics already, but how does it work mathematically? I mean, what do you know from pop physics already? I mean, please make your question more precise. I don't understand. But okay, there are no other questions. Let's move on. Now you can talk about the R component of the geodesic equation, right? But the thing is that all the components of the Schwarzschild metric depend on the R coordinate. So if you solve the geodesic equation or you try to calculate what the geodesic equation looks like for the R component explicitly, it can be very cumbersome. It can be very, very hard to do. I mean, not hard to do, but it's just a lengthy calculation. But there's a smarter way to calculate, the dependent, the geodesic equation of R actually. And how do you do that? Well, for that, you need to remind yourself that I told you in the last two lectures that if you talk about the 4 velocity or u alpha, we do know that the 4 velocity always equals, I mean, the inner product of 4 velocity with itself always equal to -1, right? What does that mean? I mean, if you expand this particular side, what does it become? It becomes GTT UT squared plus GRR UR squared plus G theta theta U theta squared plus G phi phi U phi squared. Now, what does this become? It becomes minus for Schwarzschild geometry. UT is just dt over d tau. Dr over d tau. Now, this thing would be d theta over d tau, but as we showed using the symmetry argument, that theta doesn't change. So you can just drop this term. And d phi is just r squared, and it has sine squared theta, but theta is always taken to be pi over 2. So sine squared theta is just 1, and you have d phi over d tau squared. It should be equal to -1 because it's equal to -1. Okay. Now, if you use the equation for dt over d tau and d phi over d tau from earlier, you can see that dt over d tau is e divided by 1 minus rs over r, and d phi is just L over r squared. So what do you get? You get something like this, 1 minus dr over rs over r. Now dt is just e, and you have to square it, of course. Plus r squared L squared over r4 equal to -1. And that gives you this equation if you simplify it. Okay, look at this equation. This equation looks a bit like, sorry, this is not phi, this is r. So this equation looks a bit like half of some, radial velocity squared. Now, if you recall the, expand the expression for kinetic energy that we have in classical physics, that's half mv squared. Now, if you talk about kinetic energy per unit mass, that's half v squared. So this particular term looks like, kinetic energy of some sort. So let's call it k for some time. And this equation looks like, potential energy per unit mass, of course. So let's call it V. And you can see that the sum of these two things is equal to this thing, which is a constant. I mean, we do know that small e is a constant. Okay. Now let me call this combination E because it looks like, the full total energy of this system. So from here, you can let me know if you know about the mechanics or Newtonian gravity, actually. The potential that you get is something like this. Sorry. The potential that you get is minus gm over r, but there's an extra term, something called this, and this is called angular momentum barrier. Let me know in the chat if you know about a particular result. The momentum potential that it experiences. This term, actually, this is the term that prohibits Earth from falling into the sun. Because if Earth didn't have any angular momentum, it will just get sucked into the sun. Anyway, so the thing is that, I'm sorry, wait, I think there's, wait, 1 minute. Yeah, oh, I see. So yeah, this is some potential energy. This is some potential energy. Let me call it V tilde. But this is not the potential, of course. This is kinetic energy. This is potential. in Newtonian mechanics. How do you derive potential in the general relativity that we are seeing here? Well, for that you need to differentiate this equation with respect to r. Okay, so what do you get if you do that? So the equation is E equals 1 over 2 dr over d. Not sorry, not with respect to r, with respect to tau, of course, plus. So if you, yeah, if you differentiate this equation with respect to, sorry, not t, with respect to r, yeah. Then what you get? You get something like this: d square r over d tau squared equals. So differentiate. What do you get? You get something like this. Okay, now you see the first two terms that you're getting here are exactly the terms that you get in the Newtonian gravity, right? But there's an extra term that you get in the Schwarzschild geometry. So this is like a correction to Newtonian geometry, or not Newtonian geometry, Newtonian gravity, when you talk about the full Deltron relativity. Okay. So there we have seen that it does reduce to Newtonian gravity. Suppose that if R is very, very big, such that you can drop this last term, your physics becomes physics that you get from Newtonian gravity. Okay. So if there are instances, let me know that I can, the term are you talking about? Yeah, correct. This is the force. This is not the potential, of course, because this looks like Newton's second law, right? The acceleration is equal to force divided by mass. Actually, it's force divided by mass, right? It's force per unit mass. Okay. Please repeat the third term. Which third term? This one or this one? I mean, they have similar origins. Is this how Einstein solved for the problem with Mercury? Ooh, okay, so the Mercury thing we will discuss in the fourth lecture, because the fourth lecture is about, well, my fourth lecture, because the fourth lecture is about the predictions of general relativity. Last one, okay. So this last term that you get is like a correction term, right? So in Newton's potential, in Newton's gravity, you get this potential, right? And if you want force from a potential, what do? You differentiate that with respect to r and take negative of that. So if you do that, you will get these two terms, right? So these two terms are coming from Newton's gravity. But in Schwarzschild geometry, you get this. How did you 4? And if you take negative of that, you will get negative 3g ml squared over r power 4. So that's how you get it. Okay. Anyway, let's move on. Now let's compare, this potential that you get from Newtonian gravity and this potential that you get from the Schwarzschild geometry. Okay. So how do they look like? If you plot Okay, I think I'm back. So, can you tell me where did I drop off? Did you hear me talking about the plots that I'm going to talk about? I think it did. Okay. Okay, so what I was saying is that, then these two potentials, I'm going to plot this potential that comes from Newtonian gravity, and I'm going to plot this potential that comes from, the Schwarzschild geometry, or in other words, general relativity. So, and let's see what are the differences between these two plots. So for Newton's gravity, as you can see that if r becomes very, very small, this term, the angular momentum term, dominates because it has 1 over r squared in the denominator, in its expansion or in its expression. But if r is big, then this term is like negligible and this term dominates, right? So if you plot Newtonian potential for very, very small r, it looks like this. So it means that it goes to positive infinity for very, very small r. But if r becomes big, then it becomes something like this. Because uh, this particular behavior is like this, right? Okay. Now in this particular potential, you can see that there is no there is no value of energy. So if you have a particular energy, you can see that you can come in, or you can have, a path that has, the radius that is decreasing. And this is the point at which it should stop. It cannot go to smaller radii. Okay. And it doesn't matter how much energy you have, there is always a radius such that you cannot go, beyond that radius. Okay. So that's true for Newtonian potential. If you plot this particular potential that comes from the Schwarzschild geometry, this one, it's a bit different because it looks like this. So it looks like the Newtonian potential for some radii part. So this is the Schwarzschild result, and this is the Newtonian result. All right. Now, in Newtonian result, there is the one radius here where the radius doesn't change, and this is called a circular orbit, right? In the Schwarzschild solution, there are two such points. This point has a stable circular orbit, and this one has an unstable circular orbit. Why is it stable? It's stable because if you perturb it in any direction, it will come back to the radius that it started with. But the unstable one is unstable because if you perturb it, it won't come back. It will either drift off in this direction or it will drift off in this direction, right? So a difference between the Schwarzschild result and the Newtonian result. In the Newtonian result, you didn't have an unstable circular orbit. You have only a stable circular orbit. Okay. In the Schwarzschild result, there is another thing that is different from Newtonian result. So if you have this energy, for example, this much energy, there is no radius such that after that radius you cannot go to smaller radii. That's simply not true. But that was true in Newtonian potential. There is no energy at which you can, go to arbitrarily small radii. But in the Schwarzschild solution, you do have an energy, and that energy corresponds to whatever this energy is. We will calculate these things. Okay. Now, what are these two radii? Let's call this RS. Well, not RS. Let's call this RC1. So RC means, a circular orbit radius, and this is. So how do you calculate these radii? Well, at these points, the derivative of the potential is zero, right? So what you do is that take the derivative of the potential and set it to zero. Okay. So what is the potential? So potential is minus gm over r and these two other terms. So you take the derivative of minus gm over r plus L squared over 2r squared. And then you have this next term, which is minus, sorry, not minus, yeah, minus gm L squared over R cubed, and you set it to 0. That will give you a quadratic equation for R. You can solve that quadratic equation and I can tell you the result. So you get two different answers, of course. And those two different answers look like this, right? So you get two different radii, which is not unexpected because you expected two solutions, one here and one here. You can see that the stable solution is the one where radius is bigger as compared to the smaller radius, because at the smaller radius, you have an unstable solution. So you will get a bigger radius when you use the plus sign, and you will get, a smaller radius if you use the minus sign. Okay. You can write this equation as this as well. 1 plus minus 1 minus 12 gm over L squared. How do you get to this equation? Well, you multiply this equation with this particular thing. So you multiply it with 1 minus plus 1 minus 12 gm over L, the same thing. And if you do that, you will get this particular form. Now here too, you can see that there are two solutions, one with the plus sign and one with the minus sign. If you want the bigger radius, then you want the denominator to be smaller. The smaller thing will occur when you use the minus sign. So it means that minus sign gives you the bigger radius solution. And the bigger radius solution is the stable one, the stable orbit or stable radius. The plus sign will give you a smaller radius solution. And that gives you an unstable orbit. So, so RC1 corresponds to the stable circular radius. So RC1 is the one that is stable, and stable one corresponds to minus sign. So it means that you have 6 gm 1 minus 12 gm over L, right? And RC2 is the same thing with a plus sign. 1 plus 1 minus 12, right? This. Okay, so there are two things that need to be mentioned here. If you talk about the stable radius, you can see that in the stable radius only occurs when R is bigger than 6 gm, right? Because the thing is that this denominator is always going to be smaller than 1 because it is 1 minus something bigger than 6 gm because you are dividing 6 gm by something that is smaller than 1. Okay. So it means that RC1 is always bigger than or equal to 6 gm, which means that there is no stable orbit for R smaller than 6 gm. It means that if you go closer, then to the black hole, then R equals 6 gm, then you can never attain a circular orbit. That's simply not true for Newtonian mechanics, right? In Newtonian mechanics, if you remember, if you don't remember, then you can derive this result very easily using the Newtonian potential. So in Newtonian mechanics, or in Newtonian gravity, actually, I should say gravity. If you have angular momentum L, then the circular orbit has radius L squared over gm. A circular orbit with any radius. You just need to have a corresponding L, right? So it means circular orbit for any radius. So this result is simply not consistent with this, which means that general relativity does not allow, or at least the spherical symmetric solutions of general relativity don't allow circular orbits for all radii, which is not true in Newtonian mechanics. Okay, Let me see if there are any questions before I move on. Is it not possible to penetrate the energy levels to break the stable orbit? Yes, it is possible. I'm not talking about breaking the stable orbits right now. I'm talking about how to maintain stable orbits right now. Um, okay. So what missed regarding the SO3 symmetry? Uh, so since I, got drop off from the call, I can't see earlier questions. So can you, post that question again? But if you want to ask about the SO3 symmetry, yes. So since you have spherical symmetry, it means that you have rotational symmetry, right? And SO3 symmetry is just the rotational symmetry. So yes, there is SO3 symmetry in the system. That's true. Okay. Now, I think I did discuss this. Okay. There is one more thing that I want to discuss, and that's Kepler's law. Kepler's one of the Kepler's laws. So if I remind you, Kepler's third law, you can derive that in Newtonian gravity. And Kepler's third law says that the time period for a particular circular orbit, well, it's not just for circular orbits, but let's constrain ourselves to circular orbits right now by this relation, right? Can you get this law, for from general relativity? Well, yes, you can. And let's see if that's easy to derive. So I just need to show that okay, first of all, what is the time period of a circular orbit? It's 2 pi divided by the angular velocity. Now, this is just the angular velocity, right? So it's one of your homework problems to show that this angular velocity, well, let's see. I think the angular velocity, okay, wait 1 minute. Yeah, the angular velocity is equal to gm divided by 2 pi. Sorry, wait, sorry. So it means that t velocity squared. Now, it's one of your homework problems to show that the angular velocity squared is gm over r cubed, which is not surprising, by the way. I mean, it's a various problem set too. I mean, it's gonna be uploaded later. Oh, wait. Okay. Anyway, so if you use this particular result, then you will get that t squared equals to 4 pi squared divided by gm rc cubed. I need more space. Give me a minute. Okay. Okay, so how do you show, by the way, how do you show that this is true? Well, you just use the Jurassic equation for, phi, and that's it. You don't need anything else for that. Okay, so Kepler's law also comes from Schwarzschild geometry, and the other things that we derived were having circular orbits. Is that you cannot have circular orbits for any radius. That's not in Newtonian gravity, but it's true in Schwarzschild geometry. And anything else? Yeah, and we did recover the first two terms that come in the Newtonian gravity, which are these two terms, sorry, in the potential, which are these two terms. Okay. Okay, before I move on, let's see if there are some questions. The question is that it has an SO3 symmetry, which can only claim because I know that a priori. How can I figure that out in an arbitrary? Well, you will need to see if this system has a symmetry. So yes, you are correct that we are assuming SO3 symmetry from the start, of course. But if you have an arbitrary system, you have to see if that system has this symmetry. So it's not a trivial question. You have to see that somehow. Okay, if we can't have a circular orbit at less than 6 gm, can we have other kinds of orbits? Yes. I mean, I'm have an orbit that goes like this. And, and it keeps going like that, which means that it's not a circular orbit because its radius changes. But if it goes, so you can have an elliptical orbit, for example. That's not a problem, right? In elliptical orbits, radius changes from a maximum radius to a minimum radius. That's not a problem. You can have elliptical orbits, right? But as far as circular orbits are concerned, You can only have circular orbits when r is bigger than 6 gm. And by the way, there is one more thing that I wanted to add. I didn't add it earlier. If you look at the square root, let's analyze the square root. Yes, so let me write down the expression for RC again. So RC is 6 gm divided by 1 minus, well, I mean, plus 1. Yeah, so for the circle, for the stable one. So it's 1 minus 12 gm over L squared. Now, you can only have this solution if whatever comes inside the square root is non-negative, right? Which means that 1 minus 12 gm over L squared should be non-negative, which means that it has to be bigger than or equal to 0. It means that 1 should be bigger than or equal to 12 gm over L whole squared, which means that L squared over gm whole squared should be bigger than 12, which means that angular momentum should be bigger than 12, well, square root of 12 gm. So you see that there is a bound on the angular momentum as well. If you have a angular momentum that is smaller than this particular angular momentum, you can never have a circular orbit, which is again not true in Newtonian gravity. In Newtonian gravity, it says that if you have an angular momentum, you could, right? Okay, let's see if there are some other questions. If we can't have, okay, that's various problem set two. I mean, the problem set two is, I mean, it's complete. I mean, the organizers will, decide when to release it, but I think it should be released in a couple of days at least. So also, can we find an analog for LRL vector? I mean, I don't know what you mean by LRL. I cannot find problem set two. I mean, I think it will be uploaded. How do we implement Kepler's law for relativistic objects? I mean, what do you mean implement? Uh, on the potential graph, which point is 6 gm? Well, okay, so if you look at this graph, this particular graph looks like, is a graph of the potential, which is given here, right? And you can see that this particular this particular potential has angular momentum. And these radii, these radii, they depend on the angular momentum, which is here, right? Now, there is no point on a graph that, well, there is a point on the graph which is 6 gm, but that point is not relevant. The thing is that you can attain 6 gm only if this thing in the square root is 0. Okay. So if this thing in the square root is 0, then it means that the angular momentum has to be what I told you, or what I just told you, right? So if you have angular momentum equal to this thing, then this thing in the square root becomes 0, and then your radius becomes 6 gm. So the thing is that this bound on the radius, which is, well, this bound that it needs to be bigger than 6 gm, and this bound on the angular momentum are actually related. So if I make this graph with angular momentum equal to square root of 12 times gm, right, then this point will be 6 gm, right? But it's not equal to 6 gm for arbitrary angular momenta. Only for angular momentum equal to square root of 12 times gm, this stable orbit is 6 gm. Okay, I hope that answered the question. Okay. Okay, let's move on. Now let's talk about how photons move. Now, what are the problems, with photons? Well, if I write down the geodesic equation again, so let me make a heading here, photons, and I have lots of topics to cover, so I don't know if I have enough time. Just so I need to rush through some of the things. So if I write down the geodesic equation again, you can see that it uses tau, right? Tau is proper time, right? And we do know that photons don't experience proper time. Proper time just doesn't flow for photons. I mean, the photons don't have a proper time that changes, right? So we should not use proper time when we're talking about, photon orbits. So what do we do, when we talk about photons? Well, we need to formulate equations without using proper time somehow. Okay, so one way to do it is to use Schwarzschild time or the Schwarzschild coordinate t, right? So we need to write down our equations in a form that has t but not tau. Okay, so how do you do that? Well, one way to do it is to introduce a new quantity called b, which is called the impact parameter. So if this is, a point which is called O, well, the origin, yes, and a photon starts from infinity at a particular trajectory, any trajectory, then if you extend that trajectory as if there is no interaction, then the smallest distance between the origin and the trajectory is called the impact parameter. I mean, this particular thing is also used in particle physics in scattering cross sections. Now, when the photon starts from infinity, it starts with some angular momentum and it starts with some relativistic energy, right? Which we referred to as E earlier. Okay. So the impact parameter can be written in terms of L and E like this, right? Now you do have the expressions for L and E from earlier. So if you go back, well, go very much back. So you can see that E can be written down in terms of dt over d tau and, this thing that depends on R. L can be written in terms of R and d phi over d tau. Okay, so if you use these expressions, what do you get? You get something like this. R squared 1 minus Rs over R inverse d phi over dt. Now, how did I get rid of tau? Well, this thing was actually d phi over d tau over dt over d tau. So d tau just cancels, right? And this thing does not depend on tau. I mean, it does depend on tau, but it doesn't depend on tau explicitly. So we have kind of got rid of tau from, this particular equation. Okay. Now, how do you write down the equation for the photons in terms of this impact parameter? Well, that's another homework problem for you. And you can use one of the geodesic equations. Sorry, no, it's not the geodesic equations. You can just use this thing that, yeah, this should be equal to -1, the same thing that we used earlier. So this is a homework problem to show that if you use this equation with the Schwarzschild geometry and this, expression for the impact parameter, you get something like this: 1 over b squared. Well, I mean, okay, let me write it down in two different forms. One form is this: 1 equals 1 minus rs over r inverse dr over dt squared plus b squared over r squared 1 minus rs over r. Okay, so this equation is not that illuminating, but you can write this equation down in terms, in this form: 1 over b squared. So you just divide both sides by b squared equals 1 over b times 1 minus rs over r dr over dt squared plus 1 over r squared 1 minus rs over r. Now, why have I written this equation like this? Well, because this thing again looks like a kinetic energy. So you can see that you have dr over dt here, which is a bit like radial velocity, and you have taken its square. Okay, so you do know that kinetic energy is like velocity squared. So what is this thing? Well, you can interpret this like a potential energy, right? So this is a bit like the potential energy that we had earlier, but this is for photons. Okay. So if you plot this, what do you get? You get something like this. So you get a graph which goes like that, right? Okay. So what are the coordinates of this point? So what is the value of r? Let's call it rc. And what is the value of the potential at particular RC? Wait. sorry, I think this is actually 2. I don't think so. So you're saying, let me see, there's a question. No, I think the problem was here. So this should be -2. So yeah, it's fine. Okay. Let's see if you have, yeah, it's fine now. Okay, so how do you find the coordinates of this point, which is like an unstable orbit? Well, again, you differentiate the potential. So you differentiate the potential and set the derivative equal to 0. So the potential is 1 over r squared, 1 minus rs over r, yes. And you put it to 0. Now, if you do that, you will see that r has to be equal to 3 times gm, or in other words, 3 over 2 rs, but that's just 3 times gm. So this is rc, this rc. So it means that photons only have one circular orbit, which is at r equals 3 gm, but it is unstable because it's a maximum of the potential, not a minimum. Okay. Now, what is the value of the potential at this particular energy? Well, if you just put in the value for r, you get 9 g square m square, 1 minus 2 gm, because that's rs, divided by r, which is 3 gm, and that gives you 1 over 27 g squared m squared. So that's the potential. Okay. So that's equal to 1 over 27 g squared m squared. Okay. Now, the thing is that we did say that this side can be treated as a kinetic energy, this side can be treated as a potential energy, which means that this can be seen as the total energy, right? So if the total energy equal this thing, right, then the photons can go all the way down to the r equals 0 point. But if energy is smaller than this particular point, then there is a point of return, which is here. So the photons can come in, but they cannot penetrate, and they have to go back. Okay. So it means that if energy is bigger than this energy, which is 1 over 27 g squared m squared, then the photons can spiral in. They have to go inside the black hole, right? But if photons have energy which is smaller than this, then they can go back, right? So if the total energy, which is 1 over b squared, is bigger than or equal to 1 over 27 g squared m squared, then they can spiral in. But if 1 over b squared is smaller than 1 over 27 g squared m squared, then they can go back. They should go back, actually. But you can see that this equation implies that b squared has to be less than or equal to 27 g squared m squared. So when you invert the fractions, the inequality switches. And you can take the square root on both sides to get this, right? And this equation tells you that b has to be bigger than 27 gm. So you see that this particular bound is actually a bound on the impact parameter. If you have a black hole here, well, so if you have a black hole here, right? So this Schwarzschild radius is 2 gm. There is an impact parameter, a threshold impact parameter here, which is square root of 27 gm, such that if there is a photon that's coming that has a bigger impact parameter, it can go away eventually. But if there is a photon that comes here, which has a smaller impact parameter, there is no way for it to go in, and it has to spiral into the black hole eventually. So this is what this result says, that if the impact parameter is smaller than this threshold, it has to spiral in, right? But if the impact parameter is bigger, then it can go away, right? So you can kind of say that it's not true for photons that if they don't enter the Schwarzschild, if they don't enter the event horizon, for example, here they are not inside the event horizon. They are not inside, r equals 2 gm. But the thing is that their eventual fate is to go in the black hole eventually. So you can kind of think that this is like the point of no return for photons. They have to stay outside this particular radius, which is square root of 27 times gm, and not 2 gm, which is the event horizon radius. Okay, so this is how you deal with photons. You have to get rid of tau and write your equations in terms of t, which I have done here, right? And you get this particular potential for the photons. And there is this radius at which they have a circular orbit, but it's unstable. And sometimes it is also referred to as the photon radius or photon orbit. Okay. Okay, let's see if there are some questions before I move on. Okay, no questions. Okay, now let's talk about something that we discussed last time. So last time when we wrote the Schwarzschild metric, we saw that there were some singularities at different. Okay, there is a question. So the point of no return for massive objects should be higher than that of photon. Um, well, so if you look at this particular graph that I had earlier here, so you can see that if the energy is bigger than this thing, then it can go inside, right? So the thing is that for for massive particles, it's not as simple as photons because it depends on the angular momentum actually. So if the angular momentum is bigger than a certain thing, then you cannot have circular orbits. So I just told you some time ago that the angular momentum, where is it? The angular momentum needs to be bigger than square root of 12 times gm. If it is not bigger than that, if it has a smaller angular momentum, then it has to go inside, right? Um, so for the the particles that I told you earlier about, for them it's not just about how close they are. It's also about how much angular momentum they have. It's also about how much energy they have. So for them, for the matter particles, I can tell you that if they have an overall negative energy, which is exactly like Newtonian mechanics. In Newtonian mechanics, if there is a particle that has overall negative energy, it can never escape to infinity. Because if it can escape to infinity, it means that it can go to a particular state which has zero energy, and that cannot happen if you have negative energy. So it's like the argument for bounded versus unbounded orbits. So here, for the massive objects, you need to consider its angular momentum. Sorry, its angular momentum and its energy. It's not just about how close to the black hole it is. But for photons, the relationship between angular momentum and energy is just given by the impact parameter. So impact parameter kind of captures its whole thing, its whole state in a way. So that's why it's only dependent on the impact parameter for photons. So I hope that I, answered your question, but if I didn't, let me know. Let me drink some water. Okay, so I was saying that last time we discussed the singularities that you experience in the Schwarzschild metric. So I only have like 50 minutes, so let me rush through some things. So if you remember, this is the metric that you have for the Schwarzschild geometry. And we saw that it seems that when r equals the Schwarzschild radius, which is 2 times gm, then the time component is 0. Sorry, the time component is 0. And the radius component is just infinity, right? Both of these things are bad. I mean, the metric tensor should not be 0. I mean, that's bad. And metric tensor going to infinity, that's even worse, right? Okay. But there's another point, which is r equals 0. And at r equals 0, well, time component goes to infinity because here you have rs over r, which is 1 over 0, which is infinity. But you have these two negative signs now, so it goes to infinity. And RR, that goes to minus infinity because this thing becomes 1 over 1 minus 0, and that becomes minus infinity. So that's bad as well. So these 2 points are like problematic in Schwarzschild geometry. Does it mean that you have a singularity at both of these points? Well, The answer is yes and no. Because if you say that, if you have a, by what do you mean by singularity? If by singularity you mean that the metric tensor diverges in some coordinate system at these points, then yeah, you can see that metric tensor is diverging at both of these points. So they do have a singularity at both of these points. But you have to differentiate between two things. One of those things is called actual physical singularity, and the other one is called a coordinate singularity. And what does that mean? So physical and a coordinate singularity. So physical singularity means that you can never get rid of the infinity, never get rid of the singularity. Doesn't matter what coordinate system you use, you can never get rid of that singularity. Okay. Coordinate singularity means that you can get rid of the singularity if you change the coordinates. So can get rid of the singularity by a coordinate change, right? So for example, let me give you an example for this. So if you just talk about flat space time, okay, just flat space time. So in flat space, if I write down the coordinate, if I write down the metric tensor for flat space in spherical polar coordinates, so spherical coordinates, it's d squared equals minus dt squared plus dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Hmm. Oh, wait, sorry. You're saying that for this case, GRR is 1 over. Yeah, you're right. Sorry. Yeah, you're right. This should be 0. Yeah. It's 1 over minus infinity. Yes, you're correct. Okay, but still there's a problem, as you can see. Okay, so as I was saying that um, if you write down the metric for the flat space in terms of spherical polar coordinates, you can see that if you look at this particular component, r squared sine squared theta, that's 0 if theta equals 0 or if theta equals pi, right? So it is equal to 0 if theta equals 0 or if theta equals pi, which means that if you talk about this circle, sorry, this sphere, this metric tensor is 0 at this point and at this point, because if this is theta, theta equals 0 here and theta equals pi here. So if the metric tensor is 0 at these 2 points, does it mean that you have a singularity of some sort at these points? Of course not, because you're just talking about flat space. The problem is with the coordinate system that you're using. We do know that at these 2 points, the phi coordinate is not even defined. You cannot give a phi coordinate to this point, and you cannot give a phi coordinate to this point. So there's a problem with the coordinates. There is no problem with the space itself. I mean, it's just flat space. How can it have singularities? So just like that, the coordinate singularity that there's a coordinate singularity that shows up in Schwarzschild radius, in Schwarzschild, metric. Where does it show up? Well, it shows up here at r equals rs. At the event horizon, it turns out that there is no singularity. Although the metric tensor diverges, GRR diverges here, but it doesn't mean that the metric tensor, so that there's a square, that there's a physical singularity here. Okay. Is there another argument to show that there is nothing wrong at this particular point? Yes, there is an argument to show that. How do you show that? Let me tell you. So, if you consider this path, so this is the Schwarzschild radius, which is, r equals 2gm. Okay. Let's go to a radius which is bigger. So let's go to this radius. So this is talk about the distance between these 2 points. So this distance, let's call this distance delta s. Okay. If we calculate this distance, it should be infinite if there is an actual singularity here, because we are going to that singularity. Okay. But if this distance turns out to be finite, whatever it is, but if it is finite, there is no physical singularity at the event horizon. Okay. And you can do this calculation. It's not that hard to do. So how do you do that? Well, so delta S, so you are only going in the radial direction, which means that you need to uh, integrate GRR square root dr from r equals 2gm to r equals 3gm, right? Because GRR square root is the distance, is the metric component that you use for this distance. Okay, if you can set up this integral, this will become something like 1 over 1 minus GR over R square root dr equals 2gm to 3gm. Now this integral can be done. I mean, you can try to do this integral. It's not that hard to do. And it turns out to be square root of 3gm, sorry, gm square root of 3 of 1 over square root of 3. And if you calculate it, it turns out to be almost 3.05 gm, right? So you can see that the distance between these 2 points is finite. Whatever it is, it's finite. It means that there is nothing wrong at the event horizon. I mean, there is no, by wrong, I mean singularity. There is no singularity at the event horizon. Okay. There is one more way in which you can see that there is nothing wrong at the event horizon. If you go back and look at the potential or the force, yeah. If you look at this force formula, you can see that there is nothing wrong at r equals 2gm. If you put r equals 2gm here, you will not get an infinite force or a zero force. It's just a finite normal force. Okay. So there is nothing wrong at the event horizon. The problem that you see in the Schwarzschild radius is because you are using bad coordinates. The spherical polar coordinates that we have been using are bad coordinates, not ideal coordinates to write down the Schwarzschild metric. There's another way to see this. Um, the spherical polar coordinates don't consider or don't treat the event horizon as a special radius. It is a special radius, although it's not singular, but it's a special radius. So an ideal set of coordinates to write down the Schwarzschild radius would at least talk about or at least consider r equals 2gm as a special radius, right? And there are coordinate systems like that, right? And we will discuss one of those coordinate systems. Let me see if there are some questions before I move on and introduce that coordinate system. Okay, let's see. Shouldn't I think I took that question. Is that coordinate singularity the reason why you can't see something fall into the event horizon? I will talk about that. I will talk about that. Let's move on. But I will talk about this question soon. Okay. So let me introduce, okay, but before I introduce those coordinates, let me tell you one more thing. So if you have this black hole, right, and you'd go to a very, very far away point, like r equals infinity, you can ask that what do the light cones look like? Wait, give me a minute. Okay. So you can see you can ask the question that what do the light cones look like for any outgoing light waves or light rays at this point. So we do know that in flat space time the light cones look like at 45 degrees. Okay, but if you come closer to the black hole, the light cones start to shift. They start to look a bit like this. So they kind of tilt towards the black hole. And when you are at the event horizon, the light cones are like that. So it means that, for example, if you are at the event horizon, there is no way that you are in which you are leaving, the event horizon. So you can see that in your future light cone totally lies inside the black hole. So you can see that if these light cones are getting very, very annoying, right? So we want a coordinate system in which these light cones stay perfect. So say they stay at 45 degrees. Okay. So is there a way to invent such coordinate systems in which the light cones are, at 45 degrees to each other. Okay, that's one desirable feature. Another feature I did tell you that we need a coordinate system that treats the Schwarzschild radius as a special point, and you need a coordinate system. This is the third thing that we need. We need a coordinate system in which the space-time switching doesn't happen. So I did tell you last time that this particular this particular component switches from positive to negative when you come out of the black hole. So outside the black hole, this component is negative, but when you go inside the black hole, this component becomes positive. So it becomes, so it means that the t coordinate becomes a space coordinate inside the black hole, although it was a time coordinate outside the black hole. So we also want to avoid that particular switching, right? So these three criteria are desirable. So, sorry. So no switching. And wait 1 minute. No switching. Light cones at 45 degrees. And the third thing is that no singularity at r equals 2 gm. By the way, can you tell me in the chat if you can see the echo of my own voice, because my tablet is not connected to my headphones anymore. Can you tell me if you can hear the echo of my voice? Voice is fine. Okay, good. Okay, good. That's good to know. Okay. So what is such a coordinate system that can satisfy all of these, criteria? So there is one very popular coordinate system that people use to study Schwarzschild solutions and many other solutions, and they are called Kruskal-Sekris coordinates. So, I'm just going to call them KS coordinates, right? So how do you define them? Well, the definition can be cumbersome, but this definition, I mean, I wish I had more time so that I can tell you why these coordinates are defined like that. But I can tell you the definition, and then we can discuss the properties of these coordinates. So, these, by the way, these coordinates are capital T, capital X, and you don't need to change the other coordinates. I mean, theta and phi are the same. Okay. So, but the old so these are KS coordinates. The old coordinates, if I remind you, they were T, R, theta, and phi. So they were like Schwarzschild coordinates or spherical polar coordinates with time included. So how to define these coordinates? So T equals, sometimes they're also called just the Kruskal coordinates, but Sekris is one of the collaborators. Okay. And X, okay. So these look like complicated definitions, but are they helpful? Well, first of all, you can show that t squared minus lx squared is 1 minus r over rs times e to the power of this thing. And how do you show that? Well, you have to use the formula that sine hyperbolic squared minus cos hyperbolic squared is minus 1. So you have to use that. The second thing that you can show, it's not that important, but you can show it. The second thing is that t equals rs logarithm of t plus x over t minus x. Okay. Now the thing is that if you plot this thing, so okay, uh, if you plot this thing, 1 minus rx or r e to the power this thing, if you plot that with r or against r, you get a plot like this. So this is r equals rs. And what is this? Well, this is just 1. Okay. Now, it means that 1 minus r over rs can be smaller than 1, and it can be, I mean, it can go to negative infinity because this is just going to negative infinity, but it can never be bigger than 1. That's the most important point. It means that this t squared minus x squared has to be less than, well, it can be equal to 1, of course. It can be equal to 1. Okay. So this is a very important property of these coordinates. Okay. Now, what does the metric tensor look like in these coordinates? So the metric tensor that, I mean, the Schwarzschild metric tensor, we do know how it looks like. If you use, the differentials for these coordinates using these definitions and, do some algebra and put your answers in the Schwarzschild Schwarzschild coordinate, sorry, Schwarzschild metric, what you get is something like this. So this is another homework problem that you have to do, but it's not that difficult. It's just algebra. Plus r squared. Now you can ask me the question that what is r doing here? I mean, didn't we change r to, uh, you know, other coordinate systems? True, it's true. But the thing is that using this equation, if you can solve for r, which you can using a particular function called the w function, I'm not going to go into that, you can write down r as a function of t and x. So when I write r here, sorry, when I write r here, I mean r squared as a function of t and x. And it's a complicated function. It can be written down in terms of a function called, if you're interested, there's this function called the Lambert W function. You can use that function to write down r as a function of t and x. But rest assured that this thing that's appearing here, it's still a function of t and x. So this metric tensor is in terms of the t, x, theta, and phi coordinates. Okay. Now, there are some things that stand out. First of all, there is nothing wrong at r equals 2gm in these coordinates. There is no singularity, right? So in these Kruskal-Sejk coordinates, the coordinate singularity that appeared in the Schwarzschild coordinate system just goes away. Okay. Second, so first of all, nothing wrong at r equals, well, r equals rs. Yeah. Second thing is that r equals 0 is still problematic because you can see that if r equals 0, then this becomes infinity and this becomes 0. So you get some problem here, which means that you cannot get rid of the singularity at r equals 0 using a coordinate transformation. I mean, I did one coordinate transformation, but it can be shown that this particular singularity cannot be, got rid of using a coordinate transformation. This suggests that r equals 0 is a physical singularity. And there are other arguments to show that it is a physical singularity. For example, if you calculate the distance between r equals 2gm and r equals 0, you get infinity, right? So r equals 0 is a physical singularity. And there was one more thing, which is the the shape of the light cones, right? So for photons, we do know that the line element is 0. And if photons move only in the radial direction, that means which means that this part is 0, which means that this thing has to be 0 for photons. And this thing can be 0 for photons only if this is 0. So it means that dt squared minus dx squared is 0 for photons, which means that, t equals x, or x or minus x for photons. And if you plot this thing on a tx axis, that gives you these lines, which means that the light cone is at 45 degrees, and that's what we wanted, right? Okay, so let's see if I have to introduce another thing. No change. I think that's it, right? Yeah, okay. So let me plot some of the curves for this particular line for this particular coordinate system. But let's see if there are some questions before I do that. Hyperbolic trajectories have a special spot in special relativities. There are relation. Yes. So I'm gonna talk about them. So it will turn out that r equals constant curves will be hyperbolas. So yeah, I mean for some, well, yeah, I think for all of them, yes, that's true. Is there a way to visualize this coordinate transformation? Well, I don't know about the coordinate transformation, but you can visualize the coordinate system. I mean, I'm gonna do that now. So let me write this. Oh, wait. Okay. So if you have a constant r, what do those curves look like? Well, you have to remind yourself of this equation, right? If r is constant, it means that this side is constant, right? Which means that r is constant curves look like these curves. So t squared minus x squared is constant, right? Now, well, I mean, let me write down what that constant is. I think this is the correct expression. Yes, that's, no, I think it's R over RS. 9. Now, the thing is that if R is bigger than RS, then, well, let's see. Wait, I think, did I write it down correctly? Yeah, I think I did. Yeah. So if R is bigger than RS, then this is negative, right? But if R is smaller than RS, then this constant is positive, right? So it means that you get something like, negative of something, or you get positive something. You get this thing when R is bigger than RS, and you get this thing if R is smaller than RS. Now, both of these, equations are the equations of hyperbola. So hyperbola. Hyperbola is the plural of hyperbola. If this constant or the right hand side that you get is negative or positive, that dictates that how does the hyperbola looks like. So if if this constant is negative, the hyperbola looks like this, look like these. Wait 1 minute. Yeah, look like these. If this is x and this is t, they look like these. I mean, they also exist on this side, but we won't talk about them for a reason. Okay, so this happens when this constant is negative, which means that if r is bigger than rs. So for r bigger than rs, these are the constant r curves. And this is the line t equals x. I mean, I should make better drawings here. And this is the curve t equals minus x. So they are becoming asymptotic to this particular set of lines. Okay. For less than rs, these are the hyperbolas that you get, right? So here we can say that, okay, so r equals constant curves look like these or like these. So r equals constant and r equals constant. Now, if r equals rs, what does the right-hand side become? Well, if r equals rs, then, wait, if r equals rs, then you get t squared minus x squared equal to 0, right? Which means that t equals x or minus x. But that precisely corresponds to these lines, right? Which means that these lines, represent the event horizon. So wait, let me take another color. So this is the event horizon actually. Let me use another color. Event horizon, right? Previously, I also said that there is this bound, t square minus x square less than or equal to -1. When this bound saturates, what do you get? So when t square minus x square equals 1, there is this hyperbola here that corresponds to t square minus x square equal to 1. How can you get this thing? Well, you can get this thing um, by putting r equals 0 here. So if r equals 0 here, then t square minus x square becomes 1. Why? Because this r becomes 0. So this thing becomes 1. This thing also becomes 1. So t square minus r square equal to 1. And but we do know that r equals 0 is is the center point of the black hole, right? Which means that this hyperbola, which is t square minus x square equals 1, is the black hole singularity at the very middle. Okay? Okay, that this is a very important point, by the way. I will come back to it later. Let's see if I have to say another thing. No. Okay. What about constant time curves? Well, they are actually pretty simple. So if you take this equation, uh, this equation, this equation. So what do you get? So time equals Rs. Let me copy it from this thing. Okay. Now, if t equals some number times x, whatever number that is, what this equation becomes? So t equals Rs as mx plus x divided by mx minus x. You can take x as constant and divide it on the numerator and denominator, and you get m plus 1 over m minus 1. So this line just corresponds to a line that passes through the origin, right? And looks like this. These are some of those lines with different values of m, because m just means that you have a gradient, and that gradient can be anything, right? So these red lines, they correspond to where m has a particular constant value. But we can see that if m is constant, then t is also constant, small t, lowercase t, which means that these constant m lines are constant t lines or constant time lines, right? How do you get t equals to infinity? Well, for t equal to infinity, you need to make the denominator 0. Well, how to make the denominator 0? Well, just put m equals 1. So if m equals 1, that implies that time equal to infinity. Okay. For m equal to -1, what do you get? Well, this becomes 0. Sure. This becomes, -2, but that doesn't matter because you have 0. So you have to have logarithm of 0, and that gives you t equal to minus infinity. Okay. But if m equals 1, you get t equals x. But that's this line, the event horizon that we discussed, right? So the event horizon corresponds to t equal to infinity as well. Uh, I think I'm a bit saturated here. So this, sorry, I wish I could had more room. This corresponds to r equals to gm, but it also corresponds to time equal to infinity. When time equal to minus infinity, m equal to -1, but m equal to -1 means that t equals minus x. And that thing is here. So this line corresponds to t equal to minus infinity. Okay. So this is, how you visualize the Kruskal coordinate system. One thing that I need to mention here is that this corresponds to t square, sorry, t square minus x square less than 1, and time being greater than t being greater than 0. Okay. And this red region, this corresponds to, well, let me use another color. This corresponds to t square minus x square less than 0, and x greater than 0. Okay. But you can see that in all of the, patches that I have showed you, t square minus x square is less than 1 as it should be. Okay. Now this diagram is a bit cluttered, so let's make a new diagram because then you may need to make some more points. So the allowed region is this, where this is the event horizon, and there is this curve t square minus x square equal to 1, which is the singularity at the middle. And this is also t equals infinity line. This is t equal to minus infinity line. And as we discussed earlier, that the constant time lines are these, okay, and the constant r lines are these, okay. Now, as we discussed earlier, in the Kruskal, metric that I wrote here, we saw that, that for photons, you have dt squared minus dx squared equal to 0. I actually wrote down this thing, but it can be with a constant, of course. It just tells you that the light cones are at 45 degrees. So if you want to say that, okay, there's a light ray that starts from here, it would always move at 45 degrees. That's one of the advantages of Kruskal Sacred coordinates. So if there is a light ray that falls inside, you can see that it always goes into the event horizon, sorry, into the singularity. It doesn't matter where a particular particle starts from. If it falls towards the black hole, it always ends up in the singularity. It doesn't matter where it starts from. If it falls towards the black hole, it will eventually go into the singularity, right? So you can see that singularity is like the future of anything that falls into the black hole, right? Um, I mean, in some sense, you can see that this thing kind of becomes a time coordinate, and we do know that when we were studying the Schwarzschild solution, I told you that the space coordinate kind of becomes the time coordinate, right? Which means that singularity, which is r equals 0, should be a time in the future in some sense. And this coordinate system actually tells you that in what sense the singularity is the future. Because there is no way to escape it. I mean, it doesn't matter where you start from, you will always end up in the singularity, right? Okay, there's one more thing. What about this region? I mean, does it mean anything? I mean, in the Schwarzschild geometry, it doesn't show up, right? Well, there are ways to make sense of this region. So for the Schwarzschild geometry, only this part counts. I mean, the part that I have already shown you. And I told you that t square, sorry, that t square minus x square needs to be equal to less than minus 1, right? For, well, it can be from minus infinity, that doesn't matter. But you can see that this part, okay, you can see that this part is at sorry, at positive t, and this part is at positive x. Okay. What if you include negative t and negative x as well? Well, okay. So what if you include these regions? This region and region. Well, it can be shown that if you include these regions, that there should be a curve like this here, right? I mean, I'm not going to go into the details of this because we don't have time, but this is something called Kruskal extension, right? And in this extension, these two regions, the blue and the red region that I have shaded, they do make sense. So this thing that I have made here is kind of like an analog of the black hole singularity, but for something called a white hole. So this red region is the interpretation of this region is of a white hole, right? And how to make sense of this? Well, I mean, it will require another lecture, but just like for the, wait, let's see, for the black hole singularity, anything that star goes into the black hole needs to go inside the singularity or towards the singularity. Here, you can say that anything that goes towards. Okay, so let me make another thing here. Sorry. Let me start from here and let me talk about a particle that tries to go towards infinite r. Okay, if you extend its you know extension sorry extend its path backward, you can kind of interpret it by saying that it came from this thing, this blue thing, right? And you can see that now this blue thing can be interpreted by saying that it always pushes things out. Unlike the black hole, if you go inside, you can never come back. For this white hole thing, if you are inside, you have to go out. You cannot come in, right? So it's like, so you can see that there is no trajectory that goes in this direction. That doesn't happen. I mean, you can never do that because it will like going back in time. So the white hole is interpreted as an analog of black hole, but where it's impossible to go inside that thing. And I mean, we do know that for black hole, it's impossible to come out, but for white hole, it's impossible to go inside. Okay, so that's an interpretation. I'm just being very sketchy here because we don't have enough time, but this is something that you can learn on your own, critical extension. What about this blue region? Well, if you look at this black region that I'm going to make now, this region, sorry, not, no, it's not black. 1 minute. This region, this is the exterior of the Schwarzschild black hole. Okay, so this blue region is interpreted as a parallel universe, or an extended external region, some people call it that, but I think I can just call it a parallel universe. Can you go from this black region to the blue region? Well, the only way to do it is to go through this point. Wait 1 minute. Go through this point, right? And this point can be interpreted as a wormhole that connects the black region and the blue region, right? Because the thing is that if you go from the black region to the blue region via this route, you can probably do it because it will say that if you go from the black region inside the black hole, that may allow you to, go inside the blue region. But that requires you to leave the black hole somehow. So let's not talk about that. But if you go from the black region to the blue region via this route, by going into this red dot, that can be interpreted as a wormhole. But you cannot go through this wormhole because this requires you to go through, a constant time slice. So because I told you that these lines to correspond to a constant time. So this horizontal line also corresponds to a constant time. So it's like a wormhole, but you cannot go through it. And these are called non-traversable wormholes. So you cannot go through that particular wormhole. So I'm just being very sketchy, but this is something that you can learn on your own. It's called critical extension. Okay. Uh, I need to discuss one more topic, and I only have like 10 minutes for it, but that's fine. And then we can wrap this up. Let's see if there are some questions. Okay. So hyperbolic trajectories have a special. So I did talk about hyperbola, so I think I've answered your question. Is there a way to visualize this? I think I gave you a way. How did you show light cones must be 45 degrees? Okay. So when I wrote down the metric tensor in terms of the critical coordinates, I told you that for photons, ds squared should be 0, right? And if there's a photon that's going in a radial direction, this thing should be 0 because there are no changes in the angles. There's only a radial direction, which means that for ds squared to be 0, this thing should be 0. But if you want this thing to be 0, then this thing should be 0. And if this thing is 0, then this thing is 0, which means that t has to be equal to plus or minus x plus some constant. And that's a line that's 45 degrees. So I hope that I answered your question. Let me know if I didn't. Okay. So last topic that I just want to touch upon, that topic is a big topic. I just want to touch upon that topic to give you an introduction to that topic, is black hole thermodynamics. Okay. That topic requires quantum field theory as well. So, of course, I'm not going to go into the details of the calculation, but let me just give you some qualitative results. So, in the 1970s, it was shown by Hawking and some other people. I mean, like Bekenstein and Hawking, and there were some other people involved. But main contributors were Bekenstein and Hawking. They showed that if you study quantum field theory, although I don't know if the audience here understands what quantum field theory is, but quantum field theory is, you can think of it as a field that obeys the rules of quantum mechanics, right? And when you study quantum field theory, it turns out that there is nothing such as a perfect vacuum. So it means that you can have particles and antiparticles popping out of nothing and then annihilating each other. So you can have a bubbling vacuum even if you have nothing else in flat space. Well, any space, right? So what Hawking did was that he considered quantum fields outside a black hole and he wanted to see what happens, right? It's not a totally so the gravity was not quantum mechanical in his calculation, right? Gravity was classical. So let me write this down. So in 70s, Hawking and Bekenstein did some calculations, did uh, calculations. So in their calculation, gravity was classical. So means that gravity was described by general relativity. It's you are not talking about they had quantum fields in their calculation. So this kind of is referred to as a classical scenario because there are some things, gravity itself is not calculation, to see that what do quantum fields behave like if you have, them outside the black hole. For example, a Schwarzschild black hole. It turned out that black hole can cause these quantum fields to behave in a way such that there is a radiation that comes out from the region around the black hole. So that radiation doesn't come from inside the black hole. It comes from the region around the black hole. So if this is the black hole, there are these points here from which radiation can go out, right? And because of this radiation, the black hole loses mass and eventually evaporates away, right? This particular radiation is known as Hawking radiation, and it is a very low frequency radiation for large black holes. Okay, so this radiation is thermal, which means that if you look at the spectrum of this radiation, it looks exactly like the spectrum of a thermal radiation. By thermal radiation, I mean that if there is some hot object in the room, for example, the kind of radiation that it will emit, Hawking radiation is exactly like that. But we do know that when you have thermal radiation, there is a temperature associated to that particular radiation. So does it mean that the black hole has a temperature as well? And Hawking showed in 70s that yes, black holes do have a temperature. And this is the result of Hawking's calculation. Of course, I'm not going to do the calculation because it involves, techniques from Bogoliubov transformations and quantum field theory. I'm not going to do the calculation, but the temperature turns out to be this. So this is Planck's constant, reduced Planck's constant. I hope that you're familiar with this. So it's 8 pi over g km. So this is the reduced Planck's constant, which means that it is h over 2 pi. K is Boltzmann constant. And m is mass of the black hole. black hole, right? So this is called Hawking temperature. I mean, not surprisingly, of course. Okay, but we do know from thermodynamics and temperature. So 1 over temperature is defined as, I'm saying defined because if you study statistical mechanics, the temperature is defined in terms of the derivative of the entropy with respect to the internal energy. So U is just internal energy. For black holes, internal energy is just mass. I mean, there can be other modes, but let's talk about mass only. If you use this relation, you can write down the expression for the entropy of a black hole, and it turns out to be this 4 pi. Um, well, I'll explain that. 4 g h bar. Now, the thing is that this thing is nothing but the area of the black hole. So if you have a sphere, right, its area is 4 pi r squared, where r is the radius of the sphere. The radius of the black hole is just the Schwarzschild radius, which is 2 gm. So this is just the area of the black hole. So it is k times area over 4 gh prime, right? So this is black hole entropy. I mean, this is sometimes called the Bekenstein-Hawking entropy. It is sometimes referred to as BH entropy, but the thing is that BH can mean black hole, but it can also mean Bekenstein-Hawking. It's the same thing. So both BH. Okay. Now you can see that the black hole entropy depends on its area. First of all, it's very statistical mechanics. You would know that entropy of systems depend on their volume, right? Not on their surface area. So that's a very peculiar, fact about black holes, that they have entropy that depends on their area. And this is actually a precursor to something called holographic duality, because people take the hint that the information inside the black hole lives on the boundary, but we're not going there. Another thing that is peculiar is that the black hole has an entropy, but entropy means that you have a number of microstates for any given macro state, right? For example, if there is a cylinder of gas that is at a particular temperature and at a particular pressure, there are like gazillions of states of the gas molecules that can give you the same temperature and pressure. So all the gazillion internal states of the gas molecules, they are called the microstates, and the total pressure and the total temperature, that's referred to as the macro state. And we do know that for a particular macro state, there can be many, 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 many microstates. And these microstates actually give rise to entropy. If black hole has an entropy, what are the microstates of the black hole? That's something that's, I don't know. I mean, it depends on who you ask. Some people think that we do know the microstates there, so there is no problem. But otherwise, if you are willing to accept that we don't understand the microstates of the black hole, then it becomes part of a well-known problem called the black hole information paradox. So the black hole information paradox can be, written down in different forms, but one form is to ask the question that if the black hole has an entropy, where does that entropy come from? Because I told you like 2 lectures ago, probably 1 lecture ago, that there is this theorem called the no-here theorem. So there is this theorem called no-here theorem, which says that only uh, features of the black hole that are detectable from the outside are its mass, its electrical charge, and its angular momentum. Right? If you throw something inside the black hole, the only information about that things that's gonna retained, that can be detected from the outside, mass, electrical, all the other information that this particular object carries seems to vanish. But If that's the case, which means that there is no, complexity or the other, or these microstates that you can associate to black holes, then where does this entropy come from? This is a central question. I mean, that has kept many researchers for decades, right? Okay, there's one last thing that I want to tell you, and then we can wrap it up. So since black holes radiate, it means that they lose mass, sure. But we do know that if there is a radiating body, what is the power output from that body? Okay, so if there is a radiating body, right, at temperature T, it loses power. I mean P, which means that it dE/dt, which is power. You can write down the formula for this loss of power in terms of the temperature, and it's called Stephen-Boltzmann law, by the way. So it has area A, then the power loss is minus A sigma T power 4. Now, if area is the area of this object, sigma is something called emissivity, which means that how good emitter this object is, and T is just the temperature. So this is called Stephen's law, Stephen-Boltzmann law sometimes. Well, sorry, I think sigma is Stephen's constant. Sorry, it's not emissivity. You can add an extra factor called emissivity here. But for black holes, emissivity is 1, so we don't need to worry about that. Okay, so using this formula, you can show that the black holes have a particular lifetime. So you can using this formula, you can see how much time does it take for a black hole to completely evaporate away. Okay, you have to use this formula for T, which is given here, right? And you have to use the fact that energy for a black hole is just mass, right? So it's not that difficult to show that the lifetime of the black hole. So a lifetime of a black hole. So tau is lifetime. You can do this calculation pretty simply because it's just a simple differential equation. So I'm not gonna do it. Let me know if there is some problem that you face while doing this calculation in the next lecture. So it turns out to be some number multiplied by mass, mass of the black hole cubed. So it means that the mass of a black hole goes like the cube of its mass. If I write down the full formula, you can write it down like this: mass divided by m dot. M dot is just solar mass, so mass of the sun, multiplied by this number, right? And this number is actually huge. It's 2.1 times 10 to the power 67 years, right? And you can see that how big that time is. I mean, it's much bigger than the lifetime of the whole universe. So, for example, if you have a black hole that is of the order of the mass of the sun, right? So, if there's a black hole whose mass is equal to solar mass, then the lifetime of that black hole is almost 2.1 times 10 to the power 67 years. I mean, for context, age of the universe is 1.3 times 10 to the power 10 years. So you can see that how big this lifetime of the black hole is, right? So if there is a big black hole that is evaporating, it will take much longer than the lifetime of the universe for it to completely evaporate away. Okay. Okay, so let's see if there are some questions. Otherwise, I think we're done for this lecture. And for the last lecture that I'm going to give, we will talk about the predictions of general relativity. I think we can stop the recording now if you want to.
Okay. Thank you.